Okay, so good afternoon and welcome to the people online. So for this afternoon, speaker will be Jackson Fliss from the University of Amsterdam. And this talk will be about entanglement and dipolar quantum Hall physics in Tensor Chern-Simons theory.
Yeah, great, thank you. And I want to thank the organizers for the invitation, and also it's a delight to give this presentation in person with a live audience. This seems kind of novel after like a year and a half of only online presentations, but hopefully it will become more and more normal in the future. Okay, so as was mentioned and is on the title, I will be talking about entanglement in dipolar quantum Hall physics and Tensor Chern-Simons model. And let's see here. Oh, let me try to figure this out. Okay. The end game here is to evaluate the ground state entanglement entropy in this model. But there's going to be some interesting things that we find along the way. So here is a useful roadmap of what we'll be talking about. If you want, you can take a mental snapshot of this, and that way you'll know about how far along in the talk you are based upon what I'm talking about. And at the very end, I'll discuss some loose ends and some open questions that we could address in the future. Okay, so for some background and motivation, I think it's fair to say that a central aspect of this conference is this fruitful interplay between condensed matter and high energy physics, and this interplay is intermediated by quantum field theory. And a big part of this is this low energy dogma that if I really only care about the IR degrees of freedom of a given model, then I can sort of forget about small details such like the lattice spacing or the details of the lattice, and overall I can capture a lot with continuum effective field theory. And a notable example of this are topological quantum field theories, and in particular in 2+1 dimensions for describing gap phases of matter. And you can do a lot there, right? You can get all sorts of geometric responses. You can describe the anionic statistics of the excitations. You can look at all sorts of entanglement signatures, entropies and negativities, and then you can also say look at higher form symmetries of these models. But there have been a couple presentations already in this week and maybe also last week about a growing set of models that sort of challenge this dogma of IR continuum field theory describing gap phases of matter. These all collectively go under the name of fracton phases of matter. And simply put, a fracton is just an excitation that has no mobility. It's just restricted to lie at a point. And these models might also have excitations with some restricted mobility as well. And this is often enforced by novel forms of symmetry. This is calling back to something that Shinke was talking about yesterday. These symmetries might be subsystems. They might be associated to a subsystem of space. They can also be extensive in their order, and this often leads to extensive ground state degeneracy. And sort of baked into all this is also various aspects of UV and IR mixing. And obviously, because of this, it's very difficult to incorporate these features into a continuum quantum field theory. And often you need to sort of look for new structures into trying to make a field theory that can replicate some of these aspects. And there's some really nice examples of work in this direction, notably by Seiberg and Shao in the past couple of years. And it's probably an oversimplification, but maybe in one line, you could say that focusing on the importance of discontinuous field configurations in the path integral for realizing these subsystem symmetries. A sort of separate approach, which I think is also very nice, is being forwarded by Kevin Slagle and his collaborators, where you couple field theories to some background foliations, and the background foliation provides a nice way to capture these subsystem symmetries as well. And then another approach, which is the approach that I'm going to be focusing on for this talk, focuses on tensor gauge theories. And this is mostly work done by Michael Precco and his collaborators. So the fractonic meat of a tensor gauge theory lies in engineering more constraining conservation laws. And the way you do this is you promote the electric field to a symmetric 2 tensor. And for instance, in this scalar charge theory, you would promote the electric field to a symmetric 2 tensor and obeys a, let's see if I can figure out this laser pointer on the flight there. It obeys this, oh, for the people in Zoom, I have to do this. It obeys this divergence relation here. And this implies that the dipole moment is conserved. And as a result of this, if you have a single charge, single charges can exist, but they can only exist at a particular point and just continuing along in time. They can't move around like this because that would violate the dipole moment conservation. But if I bring in a partner for this guy and I form a dipole, then this dipole can move as long as these two charges move in tandem. This dipole can move in a direction that's either along its dipole moment or orthogonal to its dipole moment. So both of these are allowed. Okay. So this is a symmetry enforced fractonic behavior in this model. And the focus of these theories has traditionally been gapless phases. You can engineer them in many dimensions, but the focus has mostly been 3+1 dimensions. But there's an interesting theory that you can also construct in 2+1D by cooking up a Chern-Simons-like term. And this was done in these couple of papers by Michael and collaborators. And this is the term that I want to focus on today. And just to give a quick summary of what we'll find, it has fractons that are enforced by dipole conservation. And then also it has other restricted mobility enforced by trace quadrupole conservation. The model is gapped. And it's going to display many characteristics that are familiar to us from fractional quantum Hall systems. And this led these authors to coin it a dipolar quantum Hall fluid. And I think one goal of this talk is to try to make this connection a little bit more explicit. Okay, so here's the theory in question, or here's the action of the theory in question. You have a scalar degree of freedom that I'm going to call suggestively A0. And then it couples to a symmetric traceless tensor Aij like this. And you form this sort of analogous thing that looks like a Chern-Simons term, except you have to involve more derivatives because there's more indices to soak up here. And this theory has a gauge symmetry, which is appropriate because this is a conference on gauge theories. And the gauge symmetry looks like this. A0 transforms the derivative of some alpha. And then Aij transforms the two derivatives of alpha, but it's a symmetric traceless combination of this. And if you couple this to a source, if you couple this to a charge A0 to a charge density, and then Aij to a symmetric traceless tensor current, then it's going to have a conservation law that looks like this. And this conservation law has some consequences. So in particular, the charge on a Cauchy slice is going to be conserved. And just like in other tensor gauge theories, the dipole moment is also conserved. But additionally, the trace quadrupole moment is also conserved quantity in this. Let's see if I can go back. There we go. Yeah, so the reason for this is that if I take a dt of Q2 here, then I can exchange the time derivative on this row for these two derivatives here. But if the symmetric traceless combination is going to kill the x squared. So this guy is also conserved.
Sorry, can you go back to the Chern-Simons?
Yeah.
What is the dimension of A0 and I?
Yeah, I will get to this in just maybe like 2 more slides, actually.
Okay.
But yeah, A0 is dimensionless and Aij has dimensions of 1 over length.
Well,
And essentially, the Aij has.
so is non-relativistic scale invariance.
No, it's not. No, and
K is dimensionless.
K is dimensionless. That's right. Mm-hmm. Yes, and we'll basically integrate out A0 and get a constraint later. Well, actually, the A0 is going to give a similar but slightly different constraint. Yeah, so if you like it, well, we'll see it soon, but it's essentially like the flux constraint in normal Chern-Simons theory, that the F has to equal equal the charge density on the plane locally, but it's a different kind of flux because of the multiple derivatives appearing here. No, because this, yeah. Yes. Yes, there is. There is more information. There's one constraint that relates the flux of Aij to this rho, and then if you take a derivative of that, then you reproduce this equation here. Yes. Well, there's no external fields here. Yeah.
Then nothing to add to this equation.
Well,
so this is also, so we studied this equation.
I think the equation that will answer your question, it will come in like 2 slides. But essentially, what's going to happen is A0 determines rho in terms of the flux of Aij, and then the time derivative of that constraint is this equation here. Yeah. Okay.
Can I ask another thing?
Yeah.
Does this theory depend on the metric or no? Is it
That's
topological in some sense?
That is a subtle thing. I've written it on R2, and I work and live in R2 for this presentation. And you can try to couple this to matter in sort of the most naive way, where you just introduce a spatial metric, you turn all the derivatives to covariant derivatives. But actually, that theory is inconsistent with this symmetric traceless gauge symmetry, essentially because covariant derivatives are no longer going to commute when you have a Ricci scalar.
Really very helpful, at least for me. If you at some point comment on a possible relation or maybe no relation to elasticity, standard elasticity.
Yeah, there will be a comment on this. Yeah, although it's a brief comment. So maybe if that does not satisfy you, we can discuss at the very end. Yeah, but to maybe finish the answer to the previous question. Yeah, if you try to just naively turn on a metric here, you find it's going to be inconsistent with this symmetric traceless gauge symmetry. But there is a theory that you can view this as a linearization about that does make sense when you turn on a metric. And so I'll talk about this at the end. Right, but for the purpose of this talk, we're just going to work on R2. That's where everything is nice and friendly, and it'll be good. And then this is relevant to Andrea's question. This is the question on units. So Aij has units of 1 over length. A0 is unitless in terms of the length, and this allows K to be dimensionless. And if you try to cook up the corresponding tensor Maxwell term, you would find that that coupling is actually relevant or irrelevant. So for the purposes of low energy physics, we're just going to focus on this tensor Chern-Simons theory. But there are some other subtleties. For instance, if you look at the dimensions of rho, you're going to find it's L or 1 over L cubed. And so if I want to interpret this as a spatial charge density, so it has 1 extra 1 over L for that. And also gauge parameters have units of length here. So in order to make sense of these, I'm going to incorporate what is right now an arbitrary scale, or actually inverse length scale that I'm going to call mu, and this will appear at various places in this presentation. And then I'll have comments about how to think about mu later. Okay. Good. So I want to start looking at quantum aspects of this model, and I'm a high energy physicist by training. So for me, that means looking at path integrals. So we're going to be looking at various path integrals, and schematically they'll look like this. integrate over A0 and Aij. Schematically, we're going to divide out by the volume of the gauge group, and we could possibly couple this to sources like this. And as Paul mentioned, A0 does nothing more than just enforces a constraint. This is a very similar constraint to what appears in regular Chern-Simons theory, but it has more derivatives. You might call this a tensor Gauss law constraint. But just determines what I'm going to call, for the purpose of this presentation, the flux of Aij in terms of this charge density. And it's a useful trick to keep in mind when we're looking at these path integrals, that if I have a non-zero charge density, I can always shift A by some fixed background configuration that solves this, and then the rest can be written as pure gauge stuff, and then do the path integral for those guys. Okay, so that's just something to keep in mind. So the first path integral we're going to look at is the following. We path integrate from time going from -infinity to some fixed Cauchy slice at t equals 0. And then we're going to fix boundary conditions at t equals 0. This what I'll call little Aij. And this path integral is going to depend upon those boundary conditions. So it's a functional of those boundary conditions, and it has the interpretation, of course, as a wave functional on that Cauchy slice. And so you can do this, and you get something that in principle depends upon these boundary conditions. But this guy is not physical because it is gauge variant. And so in order to get the physical wave function, we have to apply a projector. And the simplest thing to do is just do a gauge transformation and integrate over the gauge group. And what you find when you do that, I have spared the details here, but what you find when you do that is that this integration, for the most part, it's Gaussian, and for the most part, when you complete the square, it removes all dependence of this functional on its boundary conditions. And so what happens is the physical wave function doesn't depend upon the boundary conditions at all. But because the kinetic operator appearing here ends up being this symmetric traceless combination of two derivatives, there are zero modes in this integration that don't participate in the Gaussian integration, but they only couple linearly to the sources. And what happens is those zero modes play the role of enforcing double function constraints. And those constraints force that the total charge, the total dipole moment, and the total trace quadrupole moment have to sum to 0 on the plane. Okay, so this is also very familiar to us from writing down the wave function in abelian Chern-Simons theory, but we get extra constraints here. But importantly, because this doesn't depend upon the boundary conditions, it's just a phase. So once I satisfy these physical constraints, the state is unique. There's only one gauge invariant state on R2. And this is a fact that we will come back to later. So this is a useful data point to keep in our pocket. Okay. The second path integral I want to look at is placing it on a manifold with a boundary. I'm going to allow time to go over all real numbers, but I'll let space have a boundary that I'll call Y. And what you find is that if you write A as something pure gauge, the bulk action, in fact, is a total derivative, and so pulls back to Y times time. And well, it has more derivatives than what we normally see for edge theories of Chern-Simons theories, but this combination of a dt and then a exterior derivative along Y is very reminiscent to chiral degrees of freedom. And a useful picture of these boundary edge modes are chiral boundary dipoles. There's if you like, there's a dipole in one direction and a dipole in another direction, and these guys only move chirally along Y. Yeah. There's another useful way to view these edge theories, which is to pick a coordinate along Y, call it S, and then pick a normal coordinate in some color neighborhood around Y. And in principle, once I pull everything back to Y, I should mention, maybe in case it wasn't clear, actually, that these derivatives here are the full bulk derivatives. So it includes both derivatives along Y and derivatives normal to Y. But in principle, once I pull everything back to y, this guy is an independent degree of freedom than the guy that is a derivative along y. And so let me call it something else. I'll call it a C. And you can see that these two different boundary dipoles can be thought of as a one chiral scalar. And then there's also a scalar who has three space derivatives, but one time derivative. And this is like a Lifshitz type scaling. So the space scale is different than the time. And so you might call this a chiral Lifshitz scalar. And one reason why I'm interested in studying these edge modes and trying to figure out, what is their nature and what do they do is one useful way of thinking about the entanglement tree is as the correlations of these edge modes across an entangling cut. And this is an interpretation that we're going to come back to later. So it's useful to know what's living at this edge. Okay. But before we do that, we're going to take a small detour and talk about the gauge invariant operators in this theory. In particular, there are no local gauge invariant operators. All the gauge invariant operators are extended objects. And the simplest things you can write down at first are line operators. And then there's one very simple operator you can write down, which is you just integrate A0 along a world line. And I include a charge here, and I've also had this inverse length scale such that this charge here can be now dimensionless. And you can see that if I do a gauge transformation, of course, this transforms with a dt. And as long as either this guy is infinite in extent, or if I say compactify Euclidean time, it closes back on itself, then this guy will be gauge invariant. And the role of these guys are to modify this tensor Gauss law constraint. Essentially, it gives the flux a point source, delta function localized point source of flux. And so because of that, I'm going to call this guy a charge defect operator. Yeah. Good. Now there are also some spatial line operators. They're not extremely complicated to write down. There's a little bit of finagling to make them gauge invariant, but I'm trying to keep this talk mostly schematic, try not to bog it down with too many equations. So I didn't write out these guys explicitly, but I can tell you heuristically what they do. One is what I'm going to call the monopole string operator. So I take a spatial curve, the CS, and it comes with a charge I'll call P. And its role in life is that when I evaluate it in gauge invariant states, it ends up evaluating the total charge enclosed around in this curve. And something that's kind of nice is even though this model doesn't on its face look topological, and in fact, again, I mentioned there's subtleties and even coupling it to a metric. This, you can tell by this expectation value that this guy is in gauge invariant states, this guy has the same expectation value if I say deform this curve, as long as I don't cross any defects. So in this sense, this operator is topological. There's also a dipole string operator, also defined along a spatial curve. And I pick a fixed constant vector field on space, say in the x direction or in the y direction. And then its charges are these constant vector fields. And when I evaluate this in gauge invariant states, I find what it does is it picks out the total dipole moment in units of 1 over mu of that live inside this region bounded by CS and along the direction of V. And then finally, there's also an operator that measures the trace quadrupole moment living inside this region here. Okay. And again, both of these guys, much like the monopole string operator, have this nice property that I can deform the contour and it has the same expectation value as long as I don't cross any defects. So these are nice string operators. Okay. There are more exotic operators in this theory as well. And these operators tell us something about the fractonic physics of the model. And maybe it's good to motivate this by going back to our charge defect operators. So if we recall, these charge defect operators were integrated along a world line with A0. And we recall in Chern-Simons theory that we're allowed to deform this line because we can always soak up a spatial index here with AI. But we don't have that freedom in this model because A has two indices. And if you try to contract A with something else, you'll find that there's not a gauge invariant combination, at least not with this single A0 here. And so there's just no gauge invariant way of deforming this world line into something more general. And this is just the statement that that charge is fractonic. It just lives at a single point and it just continues at that point for all time. Okay. No. Yeah, well, we're going to, yeah, we'll do the ribbons in just a second. But there's an orthogonality constraint that prevents you from doing the twists. So yeah, that's at the bottom of the slide there. Right, but yeah, if you have two of these guys, I put them next to each other, then their product, well, in the exponent, I can take this difference in their exponents and sort of trivially rewrite an integration in between these guys. And then that gives me another index now to soak up for AIJ. And this allows me to use AIJ to deform this guy into something more general that you might call a strip operator. But it's important that you find that if I want to preserve gauge invariance, that I can only deform this guy orthogonal to its dipole moment. And so this is a restating of the fact that dipoles here have restricted mobility. They're not allowed to move side to side. They can only move backwards and forwards. And then you can start playing games. You can say, okay, I'm just going to take a general embedding of a strip in 2+1 space and ask what are the constraints based upon gauge invariance. And you can start cooking up all sorts of different gauge invariant strip operators that I've depicted some here. Some continue on forever and wiggle around. Some close back up on themselves. So this time contour is embedding has a closed contour. Some lie on only spatial regions, but can be an infinite extent in one direction and then finite in another direction. But what's important in all these operators is this constraint here. I mean, there's other things that they have to satisfy, but they all satisfy this constraint that the velocity in one direction is always mutually orthogonal to the velocity in the other direction. And this is, again, a restatement of this restricted mobility of the operators. Okay. So, so far, everything I've been saying,
Sorry,
the charges.
Can I ask you maybe a very simple question, if you can go back? So if you construct this, take these two lines, these are the vertical lines.
Yes.
So if you move it, the dipole is constant. And so this tells you that, okay, probably you can do it.
Yeah.
What about the quadrupole moment? It seems that it changes, no?
So if you move it side to side, the quadrupole moment changes. That's right. But if you move it backwards and forwards, it does not change. At least the trace quadrupole moment does not change. The general quadrupole moment in this model is not conserved. That's not a conserved quantity, so that it doesn't pose any constraints. But the trace quadrupole moment is, and that's what causes these dipoles only to move in one direction.
I see.
Yeah. So if I, here's a Q and a negative Q on space, and they have a dipole moment that runs like that. And now I can allow them to move backwards and forwards in this direction. It's their dipole moment. Does that make sense?
Remaining parallel to itself, or not?
No. Orthogonal to the dipole moment. The dipole moment is in this direction, and they can move backwards and forwards in the direction orthogonal to that.
So the dipole rotate?
The dipole cannot rotate. Well, there are some strange strip operators that you can draw that are yeah, okay. Maybe they can rotate, but I haven't quite made sense of this yet, so I won't say too much. But there are strip operators which are gauge invariant, that lie on a single time slice that are annular, because the embedding in this direction, the velocity of the embedding in this direction is always orthogonal to the embedding in this direction. So this is a gauge invariant operator, but I'm not sure what the, it's restricted to a time slice, so it's not like a dipole moving in time. I'm not sure what the physical interpretation of this operator is, though.
Okay.
Yeah.
Thank you.
I may think about so plane full of dipoles.
Yes.
And there is a continuity equation which restricts their motion, but their position costs no energy, right? So it's only a symplectic form, sort of.
Yeah.
Well, no energy, zero energy, right? You can replace their position.
They can go along one direction from zero energy, but the other direction, well, the other direction requires energy, and in this IR limit, they're just totally disallowed for them to go in the other direction. Yeah.
It's a constraint.
Yes, it's a constraint. Maybe even though this is something I'll talk about later, maybe I'll go ahead and mention this connection to elasticity. And this connection to elasticity, the dipoles correspond to dislocations, and the dipole moment is the Burger's vector contracted with an epsilon tensor. And since the dislocations can only move along their Burger's vector, well, they can move along their Burger's vector for free. That means the dipole moves orthogonal to its dipole moment. In order to move in the direction orthogonal to the Burger's vector, you have to start taking things out. You have to start making defects or interstitial defects, and that costs energy. And so that's why in this low energy limit, these dipoles have restricted mobility, at least in this analog to elasticity.
So we consider this arrow as a Burger vector, right? Or Frank vector. No, it's a dislocation, not disclination.
Yeah, the Burger's vector in this case is actually orthogonal to this guy.
Yes, this arrow which is orthogonal.
Yeah, that's right.
But short question.
Sure.
Sorry. So dislocation is characterized by Burger vector, right? Not by tensor.
No, that's right.
You prefer to write it in terms of tensor, which means and tensor is displacement, right? Displacement tensor. Yeah. But if you think about dislocation, it's a vector, right?
No, that's right. And same thing with the dipole moments here.
Can you explain? It's alternative description.
No. I think you already hit the nail on the head. It's in this connection to elasticity, the 2-index electric field is analogous to this displacement tensor.
Displacement. Yeah. Right. But alternatively, you can describe it by Burger vector if it's only dislocation. Yes. Or maybe something else.
Well, in this model, you still have charges in this model. They're just fractonic. Yeah. They just can't move.
So dislocation plus something else.
Yes.
Because dislocation, okay, let me clarify.
It's dislocations plus disclinations.
And disclinations.
Yes.
They combined, so there is a Burger vector and Frank vector, and we can build out of it a symmetric tensor, right?
Yes. Yeah. Okay. Any more questions? Cool. Right. So I have mostly focused on infinitesimal gauge transformations, which means that nothing is quantized in terms of integers in this model. And the charges aren't quantized, the level's not quantized. And this is a perfectly fine model to look at in the continuum. But now I want to sort of venture into what happens or what do I have to do to start seeing charge quantizations and level quantizations. And as we all know, that is sensitive not to the algebra, but is sensitive to the global structure of the group. In particular, we know that if I'm dealing with a U1 as opposed to an R. And this is where this length scale starts appearing here, because we remember that the gauge transformations themselves had some units to them. So in order to exponentiate this into a group element, I need to incorporate this inverse length scale here. And so part of this slide and the next slide is trying to make sense of what this length scale is, but also try to make sense of more broad charge quantizations. But already, if I am allowed to promote this to a compact group by using this inverse length scale, then I can construct large gauge transformations. For instance, if I compactify time, and I can have large gauge transformations that wind around that are going to quantize the charges of the charge defect. So that tells you that the fundamental charges of this model are quantized. But for the other string operators and for the level, it turns out you have to do something a little bit more exotic to quantize these guys, and a little bit more, a little bit more exotic. And to do this, I'm going to take some inspiration from this XY plaquette model, or what Shunke yesterday was calling the Bose metal model, with an asterisk, because I am going to include here, for Zoom guys, I'm going to include these extra two terms in the Hamiltonian. And what these extra two terms do for me are they're going to allow the continuum description of this model to be rotationally symmetric, which these tensor gauge theories are. There's other tensor gauge theories that are not rotationally symmetric, which would be more applicable to the original model. But for the purposes of this model, we're interested in this rotationally symmetric limit. And what's interesting is that when you add these terms, they break almost all of the subsystem symmetries that Shunke was talking about yesterday. And there's an extensive number of these symmetries in one direction, an extensive number in another direction, but these interaction terms break those explicitly. And what's left over, in addition to the normal U1 shift symmetry of phi, is a dipolar shift symmetry, where I am allowed to shift by some parameter times a vector, or times the lattice vector in the x direction, or the same for the y direction. And because phi is appearing as a phase variable in this Hamiltonian, and all the correlation functions involve e to the I phi's in this model, this shift symmetry is just by formulation compact. The shifting this guy by 2 pi is the same gauge transformation. So this guy has a compact dipolar shift symmetry in the lattice theory. And then if I go to the continuum theory, the Hamiltonian looks like this. I rescaled phi by the lattice spacing to keep the units of this coupling constant the same, and also to write this shift symmetry in a suggestive form. So now it looks like the types of shift symmetries that would appear in these tensor gauge theories, but now in the continuum limit, this symmetry is no longer compact, because if x is a continuous variable, then e to the I something x does not have to be single valued. So in the continuum, we might think that, okay, we're just left with an R tensor gauge theory, but I'm going to propose something maybe a little bit kooky, but maybe we're interested in still organizing things based upon the lattice symmetries. We're maybe interested in organizing things based upon the integer charges that came with the compact lattice symmetries, but maybe we're interested in other continuum aspects of this model. Okay, so we're going to try to strike a balance with this continuum lattice formulation, and the way I'm going to do that is I'm going to say that this mu should be thought of as 1 over the lattice spacing. And whenever I construct gauge transformations, I'm going to view this mu times x as an integer in those gauge transformations. And if you allow this to happen, then what you find is that there are indeed large gauge transformations that are going to quantize the charges of these string operators. The p of this m, this is going to quantize the components of this v in terms of this lattice, in this case it's a square lattice, and then also quantize this nu, but it's also going to quantize the level. Okay, so this is if you like, a nice mechanism in this theory to quantize the things that were already quantized in the lattice theory. Okay, good. So if we allow this lattice spacing to creep back into the continuum model. And there's some interesting things that happen. And this is where I think a lot of the interesting quantum Hall physics starts popping out. In particular, there are large dipolar gauge transformations that shift dipole moments by k times an integer in terms of lattice spacing. And this is fine because all the gauge invariant operators were exponentials of dipoles coming with 2 pi over k. And this means that the gauge invariant operators don't see this shift. Another way of saying it is that dipoles of dipole moment k times an integer times the lattice spacing are not visible to gauge invariant operators, and all the physical dipoles fall into equivalency classes of the zk. And so one way of interpreting this is that the vacuum is actually a condensate of what you might call a longish dipole. Right? I mean, it's still short in the sense it's still order 1 of the lattice spacing, but it's anything shorter than k is like a physical dipole. Anything longer than k or anything k times k is allowed to become transparent. And as Paul was asking me to elaborate on, and as I mentioned before, there's a rich connection here between tensor gauge theories and the elastic theory of 2D lattices. And there's a lot to be said there. I already mentioned this idea about the Burgers vector providing the motion of a dislocation along a Burgers vector providing a natural explanation for the motion of these dipoles. And so in this correspondence, you might think that this dipole condensation is related to a dislocation condensation. And there are lots of neat papers about condensation dislocations and how you can mediate these through a supersolid, and this signals a quantum melting transition of the lattice. I'm a little bit puzzled about exactly how this mechanism in this model realizes this melting transition here, because I'm not sure what mediates this. Well, in these models, it's mediated by a supersolid. I'm not sure what's the same role, but there's a very analogous mechanism in this model. So it's an interesting connection. And when I allow these longish dipoles to condense, then I suddenly restore mobility to the fundamental dipoles and the charges. And the way that works is the following. If I have a shortish dipole at some position, I can pop a longish dipole out of the condensate, and I can glue these guys together to make a longer dipole. But then I could have taken off a longish dipole on the other side and popped it back into the condensate. And what this allows is this short dipole to hop along this direction that it previously was not allowed to. So in the macroscopic sense, these guys now regain their mobility along the directions that they previously were not allowed to move. And this is also true of the charges, of course, because you can always pop these guys in and out of the vacuum and then move them along in either of those directions. Okay. So at the end, there's one more interesting point about this condensate, which is that so far we have charges that now have gained mobility, and we have dipoles that have now gained mobility. But now I really want to think about this model as being a model composed of whose fundamental constituents are really the dipoles. And the way to think about this is that the charge neutrality constraint on R2 means that if I have any fundamental charge here, it has to come with a partner somewhere. And I can imagine, say, at this corner, having a positive Q, negative Q, and then start condensing the long dipoles that separate these guys. And eventually what I'm left with is the remainder that cannot be condensed. It's some short dipole here and a short dipole in the Y direction here. And so this dipole condensation also allows you to exchange the fundamental charges and really think about them as in terms of these small collection of small dipoles. So now we have the effective degrees of freedom in this model are these dipoles and now regained mobility. And they also have abelian anion statistics that you can determine by taking these dipole string operators that I talked about before and wrapping them around a dipole. And what you find is that if I take an X direction dipole string operator and wrap it around an X, then I get something that looks very similar to an abelian statistical phase, 2 pi over K. And same thing for the Ys. And then these guys are mutually local, okay? So now it's really beginning to look like there are just two collections of abelian topological order. And this is, I think, probably the most explicit that you could state that this model, at least when you allow the gauge symmetry to be compact, and this model looks like a quantum Hall fluid of dipoles. Okay. So I want to now transition into the last act, and we're going to try to push or you have a question?
Yes.
Yes.
In your original action, which was this kind of Chern-Simons, generalized Chern-Simons, the Hamiltonian is 0.
The Hamiltonian is 0, that's right.
So how would you account for this condensation? I mean, you assume there is some extra dynamics that you didn't clarify and that creates this possibility, or?
No. By the condensation, I just mean that there are objects, these what I'm calling longish dipoles that are invisible to all gauge invariant operators. They're the same as the vacuum. So it's, if you like an analogy to ordinary Chern-Simons theory, they're like anions of charge K, right? These guys are not visible to any other, any other operator is local to these guys. And so there's no way to distinguish them from the vacuum. So you might as well view the vacuum as just a superposition of all possible collections of these guys. And in that sense, these it's nice backdrop music. Yeah, in that sense, I'm thinking of these dipoles that have k times and integer times, or lattice spacing as condensing, in the sense that there's no gauge invariant operator that can distinguish them from the vacuum. It's not a maybe condensing implies something continuous, or implies an active. It's like an active verb. There's not a dynamical process where these guys are condensing. It's just that I'm at 0 temperature and the strict IR limit, and the vacuum is a condensate of these longish dipoles.
It's come from the fact that the K is quantized, or?
Yes. Yeah. It came from the compact symmetry group. Okay. And yeah, that's the real key to this. Now, at the end of this, I'm going to walk back. I'm going to say what happens when we don't allow it to be compact, and try to rephrase these results in terms of that. But I think a lot of the interesting quantum Hall physics, at least whenever I was working this out, a lot of these interesting quantum Hall physics comes out as a result of making the symmetry compact. So I think it's worth exploring. But then you can also say, well, maybe I'm not willing to go down that road. Maybe I'm not willing to make it compact. I just want to do simple infinitesimal gauge transformations, the symmetries are, and then you can do that, and it's a fine theory, and I'll tell you what the entanglement entropy is for that as well. But it has a different interpretation than the theory with the compact symmetry group.
And that if I realize this model on a lattice, then it's natural somehow to have a compact group, and then I have this phenomenon.
Well, that's a little bit tricky. I mean, this XY plaquette model that I used as an example, because phi here is a let me go back to the model. Because phi is an angular variable, this symmetry is naturally compact, and it is true that this once I go to this rotationally symmetric point where I include these deformations of the Hamiltonian, then in the continuum I can dualize this into a tensor gauge theory. This is something that's outlined in, say, Seiberg and Schao's paper. But it's not, I'll be careful and say, it's not clear to me how to realize the tensor Chern-Simons theory from a lattice model, right? So I'm taking an inspiration from this, and I want to see what happens if I continue to allow the charges to be integers based upon this. But I do want to caution that there's a leap in the logic. It's I don't know how to realize this tensor Chern-Simons for, say, this type of spin Hamiltonian. That's right. Well, I'm going. My Hamiltonian is 0. Yes. Yes. Well, as I said, this model is not the tensor Chern-Simons theory, right? This model is actually gapless, right? This model its continuum model is this tensor gauge theory, which is gapless. So it's not the same model. I'm sorry, I had a hard time understanding what you just said.
I'm saying that this is Hamiltonian, but you can transform it to Lagrangian.
Yes.
Then will be kind of PQ dot term, I mean, time-dependent term, and that's what you have in mind, right?
Well, yeah, but that again, that
you
Lagrangian,
have in mind only Poisson structure, right?
No, that Lagrangian is going to give you the tensor Maxwell term if you dualize this to the tensor gauge theory, and that term is in principle a separate term from the tensor Chern-Simons theory. The tensor Chern-Simons theory is more relevant in this dimension, but yeah, again, it's not very clear to me how to realize this tensor Chern-Simons theory directly from this model here. Yeah, so I mean, I think that is definitely a gap in the understanding, but I'm taking inspiration from the symmetries of this model. Okay, but again, at the end of the day, I'm going to comment what happens if I don't do this. What happens if I just stick with the vanilla R symmetry? Okay, good. So now I want to, I want to go back to this fraction quantum Hall analog, and I want to try to test it in a way that is familiar to me, maybe is and familiar to other people in this audience, by looking at its ground state entanglement entropy. And this is the obligatory slide that appears in every presentation about entanglement entropy on one slide. The idea is that we have a state defined on a Cauchy slice. We pick out some region A and divide it off from its complement. A complement here, we're going to suppose that the Hilbert space factorizes with respect to this. And then given our favorite state psi, we can trace out a complement, and this forms a reduced density matrix. This guy is generically mixed, and so it has a non-zero von Neumann entropy. And von Neumann entropy is going to tell us some uncertainty of the state upon losing information from a complement. And so this is what we'll call the entanglement entropy. And as Dimitra reminded us 2 days ago, in 2+1 dimensions for gap systems, this has it's very well known what forms this can take. There's a term that scales like the area of the boundary of this, what I'm going to call the entanglement cut. And to soak up the units of this guy, I need to introduce a short distance cutoff. I'll call epsilon. And this term here depends sensitively on which short distance cutoff I choose. Okay, so this guy is not universal to the details of the UV physics. But there is a term that is universal, and it's this constant because it is insensitive to rescaling epsilon. And this is collectively known as a topological entanglement entropy. And for abelian topological phases, it is 1/2 log k, where k is the total number of anyons. Okay, so this is all well and good. This is what we might expect if you're looking at abelian topological phases. But there's an important subtlety that was sort of skipped over in the last slide, which is that this tensor factorization is just actually not true in the present situation. And in fact, even in regular continuum quantum field theories, it's quite subtle because of the sensitivity to the UV physics at the entanglement cut. But even in a regularized sense, in gauge theories, this tensor factorization according to subregions just doesn't happen. And this is because gauge constraints make it impossible to localize information into one subregion. But there's a simple diagnostic of this in our present theory, because so there's a brief lapse in the microphone. And we remember that on R2, there's only one gauge invariant state. So the dimension of that Hilbert space is 1. And so it better be the case that if this were to be an inequality, that both these must be one-dimensional. So then you can ask, what is the dimension of one of the factors? And one thing to do is when you look at the generator of gauge transformations in a subregion, you find that it has a non-zero boundary term. It looks schematically like this. There's other terms where you have to symmetrize over I and K, and there's a term that comes from subtracting off the trace portion, but schematically it looks like this, and they're all integrated along the boundary of this entanglement cut. And you say, fine, I'm just going to declare HA to be states that are annihilated by that guy because I want them to be gauge invariant states. But it turns out, if you look at the commutator of these charges, you find that it's centrally extended. And that means you can't set Q to 0 as a constraint. You have to keep it around. And you're left to conclude that instead HA must carry representations of that algebra. And so you start looking at this algebra, trying to see if you recognize it. And with a little massaging, you find that it's actually isomorphic to two U1 Kac-Moody algebras. And they're labeled by these I and J indices. You can take I and J to be X and Y. And they're mutually commuting because it's delta ij here. And you can heuristically think that these algebras are like the algebra of the oscillator modes of these dipolar edge modes at the entanglement cut. Okay. And so these representations are now representations of a U1 Kac-Moody algebra, and the representations are labeled by the zero modes of these guys. And if you go back to the expression for Q and you plug in what corresponds to J0, you're going to find that that guy is actually what appears in the exponent of the dipole string operator. And this dipole string operator wraps the entanglement cut. And so this tells you the zero modes are in fact the total dipole moments contained in this region A, okay, in the ith direction. So now you have some Kac-Moody algebra. You have its representations that are labeled by dipole moments, but importantly, each of these representations are infinite dimensional. And so it just can't be the case that this one-dimensional gauge invariant space cannot be the tensor factor of these two guys. Yeah. Okay, so that is a stark inequality there. So the fix to this is that we're going to embed the physical Hilbert space into this tensor factor, and then we're going to do the trace in this larger, what's called an extended Hilbert space. But because by definition, this larger extended Hilbert space is gauge variant, we have to take some care to find the physical state inside of it. And the way that we do this is we're going to say this state maps to psi, and we're going to identify it by imposing the gauge invariance by hand. And what this means is that gauge transformations, infinitesimal gauge transformations on one side have to correspond to an infinitesimal gauge transformation on the other side. And in terms of the currents, it implies this. And if you are familiar with boundary conformal field theory, you might recognize this as the condition that determines an Ishibashi state. And so once I specify the representation by specifying the dipole moment inside of A, then I find that the solution is actually unique, which is good because we know there's only one state. And it's basically a tensor product of these Ishibashi states. Right, so this leads to this nice little picture that I like, that the bulk entanglement of the Chern-Simons, the tensor Chern-Simons theory is equal to a left-right entanglement of Ishibashi states. It also mirrors familiar aspects of ordinary Chern-Simons theory. But importantly, this also reduces down to a known calculation because there are many instances of people evaluating left-right entanglement entropies of these states, and this is not the unique paper here, but I think it's a nice one where they do these sorts of things in pretty gory detail. It's a paper by Shweta and Shunji Matsura and Shinsei. And yeah, I think it's a nice paper if you want to know how these calculations work. Okay, and again, my goal is not to bore you down with equations, but I think so I'm not going to reproduce these calculations, but I will just mention some broad features that I think are important here. For one, these Ishibashi states have divergent norms. So in order to make them a normalizable vector in the Hilbert space, you need to supplement them with a regularization. This is where this epsilon is going to appear. And the way that it's normally done is you smear them a little bit in Euclidean time, less epsilon. And as was pointed out a couple times, very smartly, the Hamiltonian in this theory is 0. So you have to supplement this with a Hamiltonian. And then you have to show that when you supplement it with this Hamiltonian, that the universal terms in the entanglement entropy don't care about the details of that Hamiltonian. It only affects the area term, right? The non-universal term. My battery is running low. Well, that's okay because we are near the end, but maybe we can see how low it is. Well, anyways. Do we want to take care of this now, or do we want to just cross that bridge when we get to it? Yeah, well, I think it's because, okay, good, there we are. Right, so, yeah, let me try to pick up where, right, so you have to supplement this with a Hamiltonian and then show that the choice of the Hamiltonian only really affects the area terms. This is done in the paper version of this. I'll just mention that the simplest thing you can do is just take the bilinear of the currents, right? This is a positive operator, and it correctly regulates the state. And when you do this, you find two basic features in, say, like the Renyi entropy. One is this Dedekind eta function that appears in many contexts that involve Bose-Einstein degrees of freedom, and this essentially comes from summing over all the m not equals 0 oscillators of the edge modes, or of these currents. And then there's a theta function that appears that comes from this, basically the compactness of the group. It comes from summing over all the equivalent dipoles that are identified by k times an integer. And so it's the status function that really knows about the compact structure of the group. Before we evaluate this, I want to present the alternative picture of this, which is that these guys also appear as the thermal partition function of this edge theory that I mentioned before. And you know, it's a familiar cartoon, but I'll just briefly say it. It's you prepare the state by path integration. Oh, yeah, this guy's slow. Okay, you prepare the state by path integration up to a time slice, and then you divide into A and A complement. And then the reduced density matrix is taken by taking the ket, which is the top portion of this in Euclidean time, identifying A complement, and then now this is something that depends upon boundary conditions here. I'm going to regulate the generation of those boundary conditions with some geometric regulator by cutting out a cylinder of epsilon. And then when I do the trace row to the end, this glues all these together cyclically. And schematically, what I have is some path integral. I've sewn out a cylinder has a radius in Euclidean time of 2 pi in epsilon. And so since we know that the theory pulls entirely back to this boundary, this is equivalently the theory of these edge modes with a periodicity in Euclidean time, and this gives us a temperature that depends on epsilon. And in this case, this Jacobi theta function arises from the winding modes of di phi that can happen when we allow the symmetry to be compact. Okay, so again, the theta function is something that tells us that the symmetry is compact. Okay, so you take the n equals 1 limit, you take the epsilon going to the limit, and the coup de grace is that you get kind of what you expected. You get an area term, some coefficient that is not necessarily meaningful because this epsilon is sort of arbitrary, but then you get, importantly, 2 times 1/2 log k, and this is consistent with this interpretation that this phase is really 2 separate abelian topological orders with k anyons. Okay. You look like you have a question. Yes. Yes, when I allow the symmetry to be compact, it follows from large gauge invariance underneath large gauge transformations in a very similar way to normal Chern-Simons theory. Yeah. But if the symmetry is not compact, then k doesn't have to be an integer. And in fact, that's this slide here. Yeah. So now, if you are not as convinced about allowing the symmetry to be compact, that's fine. You can still work with this model with a non-compact symmetry. You just don't get any of these charge level or dipole quantizations. And importantly, the vacuum is no longer has this interpretation of a condensate of dipoles. And because of this, there's no mechanism to allow hopping of the short dipoles of the charges. So everything remains restricted. The charges remain restricted. They remain fractons, and the dipoles have this restricted mobility orthogonal to the dipole moment. And so you might call this a fractonic insulator. And if you ask what's the entanglement signature of this phase, then this is something that we can actually easily evaluate because, as I mentioned, really it's only the Jacobi theta function in those guys that really knows about the compact symmetry. And so you can just remove that sum. And what you'll find is that you get three terms. You get this area term that sort of always appears with an arbitrary coefficient. You get a log term here, and then you get a constant term as well. And unlike previously where the constant term was universal, because this log appears, this guy cannot be universal, because if I shift my definition of epsilon, if I shift my UV regulator, this shifts the log by a constant. And so this guy also is sensitive to the UV regulation. So the universal information of this entropy is actually the coefficient of the log, but it's a very coarse signature. In fact, when you go through the calculation, you really find that the only thing it's telling you is that it's 2 times 1/2, and that 2 is because there are 2 polarizations to the symmetric traceless tensor. And yeah, I'm like 2 slides. Is that fine? 2 slides? A closing slide. Yeah. Okay. Well, there are many things to do. Yeah, there are many things to do here. There's subtleties that were mentioned about coupling this to curvature or coupling this on general backgrounds, which puts it a little bit in tension with this interpretation of quantum Hall physics, because we know that, for instance, the Hilbert space of abelian Chern-Simons theory doesn't care about that. But there are other interesting connections between quantum Hall physics and tensor gauge theories. And yeah, well, I will allow you to ask me about that later if you want to. And then there are other aspects you can look into. You can look into these gapless tensor gauge theories in higher dimensions, and try to ask what you're going to get, what entanglement signatures you get out of that. There are additional things you have to evaluate because of the bulk gapless modes. And then you can start asking about more exotic gap systems. And I'll just say that I think right now the field theory descriptions, there's still much to be done to understand fracton phases in terms of field theory, but I think right now we're starting to get to a point that they're mature enough that we can start answering these types of questions. I think this is a very fruitful thing to do in the future. Okay. Thank you.
Thank you. So we have had a lot of questions during the talk. Do we have some more?
I have a couple of questions. Can you go back to your slide about the entanglement entropy for the fractonic insulator? Is the log correction due to gapless modes in your bulk? Because usually the log correction are not that.
No. This is it's still a gap theory in the bulk,
Yeah.
but yeah, the short answer to your question is no. It's the only thing that's really appearing here are the gapless modes on the boundary.
Okay, on the boundary.
Yeah.
Yeah, about now these virtual cuts that you have, right? So you showed there are these Ishibashi states.
Yes.
Now, if I remember correctly, so these virtual modes are somehow also related to the real edge states, right? So
Yes.
and you showed that there is a Lifshitz scalar theory, which is not Lorentz invariant. So
Yes.
actually, you would have a scale invariant, but not conformal invariant edge theory, right?
Actually, there is a very strange form of conformal invariance that you can find in this theory. It's a little bit hidden, but if you look for it, you'll find it. And actually, it's a little bit fortuitous, but also maybe a little bit engineered that this bilinear of currents, the simplest bilinear of currents that you can construct that I'm using to regulate this oh, my mouse is not working, right? Because we unplugged it. This guy here that we use to regulate this, the simplest thing you can write down actually in terms of the edge modes, is the thing that generates the conformal symmetry of the Lifshitz theory. Now it's a little bit subtle because, as I said, this algebra is isomorphic to the algebra that we found. If I think about D alpha as being like the edge mode, it's isomorphic, but there's some field redefinition cooked into that isomorphism. That's why this conformal invariance is a little bit subtle to find, but it's there.
Okay.
Yeah.
It's not the warped CFT.
Sorry, say that again.
Is a warped CFT or no? Well,
No, I think it's just a general
generalization.
CFT. Yeah.
Okay. Thank you. Thank you.
Yep.
Minded question. I mean, the usual Chern-Simons theory, I can think of as an effective theory coming from a microscopic theory of non-relativistic fermions.
Mm-hmm.
Is there a way of thinking of this as an effective theory of some microscopic theory? What would that be?
I think the most promising thing that I've seen is this work by Andrei Gromov, which okay. I don't want to say too much because I don't want to wrongly represent that work, but it can be seen as an effective theory of vortices in 2 dimensions. Vortices, yeah. But as I mentioned before, it's realizing this with, like, say, a microscopic spin Hamiltonian, I think is pretty subtle. It's yeah.
More questions from people online? Okay, so thank you very much. And have a nice weekend. We will reconvene on Monday.